Hey folks. Okay, this time around I want to look at type checking in particular. So looking at types, looking at type compatibility, looking at type conversions. So we want to think about what kinds of syntax we have to worry about, what range of data types we're going to support, right? All of these things that are very commonly associated with program or with specific languages. So you're as a programmer, one of the first things you notice is the suite of different data types that are available to you, how you have to use them, what kind of conversions are available to you. So this is something that's often a very visible part of the language as far as the developer is concerned. All right. Again, we've got the notion of static typing, where the types are fixed at compile time, fixed dynamic typing, where it's not set until the program runs, but once you set a data type for a variable, that's it. That's the type forever. Or we look at dynamic typing, where the type is fluid. It's more associated with the value that's currently in a variable than with any specific, rather than having a specific data type for the variable itself. So one of the things that we're really interested in is how you go about converting from one data type to another. And all the time as a programmer, you get somebody to enter something as a string and then convert it to an integer or to a real, or you've got an expression where it's a mix of real numbers and integers, and you want the result as a real or you want the result as an integer. So there are all sorts of points where we have to think about where a conversion is going to take place. Or maybe we've got a class that represents temperatures, and for some reason we've got one that represents them in Fahrenheit and another one that represents them in Celsius, and we want a conversion mechanism between them. Right? So there's all sorts of places where we want to think about the conversions between different data types. So implicit conversions are the ones that are taken care of sort of for us by whatever code the compiler generated for our program, right? In our high-level language, I did something like take an integer value and assign it to a floating point variable. And behind the scenes, the compiler looked at that and went, oh, I better change that 3 to a 3.0 and then assign it. Right? So these are the ones that take place implicitly, take place automatically. Very often we don't think about it so much, but it's happening in repeatedly in some of the arithmetic expressions that we create. For instance, if I do something like x is equal to a plus b times c minus d over e, and some of them are floats and some of them are doubles and some of them are longs and some of them are ints, then as the compiler is going through, it has to figure out for each of those different operations that takes place, what kinds of data types are my operands, and how am I going to convert that? How am I going to sort of implicitly convert those into something that are compatible with one another? Or am I going to throw an error instead? Say, I don't have an implicit conversion available for this. You've got to tell me what to do. So the implicit conversions are taken care of for us automatically, which means that there's a potential problem there as a programmer if we're not anticipating the meaning or the implications of that implicit conversion. But explicit conversions are the ones where, as a programmer, I go in and stick some kind of code in that says I want this thing treated as this other data type. So, well, for some reason I've cast 3 to an int here. So the idea is we've got some data value and we say I want this treated as type whatever it might be. This should probably be something like float, where you give a data type and say whatever's coming next, I want that converted to a different data type. So if I want 3.7 explicitly converted to an int, then I might say int 3.7. And so you're telling the compiler to stick in whatever code is necessary to do that conversion for you. And as long as the compiler knows how to do that, you're okay. So there's got to be some way for the compiler to know what conversion that actually, what code to actually use to carry out that conversion. So sometimes there's a set of built-in conversions that you can make use of, things like the int or float or whatever. And other times a language may allow the programmer to explicitly say, here's a chunk of code to convert a this to a that. Right? So depending on your language, you may or may not be able to do that. Now, we do have to be aware of the implications of these conversions. So there are times when what you're converting to and from are more or less the same kind of abstract data type. It's just one of them has a bigger storage area than the other. So for instance, if we're looking at ints and longs in something like C, where they're both representing, binary integers, they're both using 2's complement representations. It's just one of them's got twice as much storage space as the other. So if you're going through and copying, from A into B in this case, then you can say, okay, well, if A is negative, just pad out with ones, and if A is positive, just pad out with zeros on the left-hand side, let's say, and we'll get an equivalent representation. So it's nice and easy to carry out the conversion. So this is what's referred to typically as a widening conversion, where you're going from a smaller storage space into a larger one. A narrowing conversion is going the other way, where if I've got some value in B and I'm trying to store it in A, and of course B's got way more storage space available to it, so whatever's in there might actually be too big to fit in the space that's available in A. So the idea is these narrowing conversions, you've got the potential loss of data because not all of whatever's on your right-hand side fits in whatever's on your left-hand side. So in a case like that, you've got to know how it's going to carry out that conversion, right? What kind of data it's actually going to chop off to get this thing to fit. So compilers will usually give you warnings about narrowing conversions because you've got the possibility of lost data, but typically they don't give you warnings about widening conversions. There's a few kinds of narrowing conversions that aren't necessarily obvious. These are things that you might well have run across over the last couple of years, but if I've got something like an int and I've got a float where the float can hold numbers that are way bigger than the numbers you store in an int, and then you say something like, okay, well, I want to assign I to f. And ordinarily, when you think about assigning an integer value to a floating point value, you're going, okay, well, if it's 3, then we'll change it to 3.0, big deal. If it's 17, we'll change it to 17.0, or represent it as 17.0, big deal. The problem comes in cases where you've got the same amount of storage space for, let's say, the int and the float. Let's say they're both 32 bits. The float actually uses some of those bits to represent the exponent, so it's going to represent some bit sequence times 2 to the power of whatever. So it's got some bits out of the 32 set aside for representing the exponent, whereas the int is using all 32 bits to represent kind of the absolute precision of whatever integer value it's trying to store. So you've got, in this case, 32 bits of precision for your integer, but who knows, maybe only 24 or 26 bits or something like that for the float. And so if you assign your I to f in this case, assign your int to your float, you can actually lose precision. You can wind up with a less precise integer value stored in your float. So it might effectively wind up chopping off those last few bits of the integer. So there are some narrowing conversions that aren't always obvious. All right, if we've got potential conversions between different data types, we need to know when types are and are not compatible. When can I use two different data types as part of some operation? So what you're interested in are whether the two, or however many operands you're using, whether all of the operands are of an appropriate type for that particular operation. So again, if we take our typical float and int example and I do something like 5 times, you do our int times our float, or pardon, sorry, I'm mixing up my example here. Let's say we've got our float x that's going to be the target for an assignment. We've got an integer y. We're doing 5 times y and then assigning it to x. Okay, so in this case, the two operands of our multiplication are both ints, it's probably going to do integer multiplication. And then we're assigning the integer result of that to a floating point variable. So at that point, when it does this assignment, it's going to have to go through and carry out some kind of implicit conversion from int to float. But again, we need to go through and look at the two operands we're using for our multiplication, make sure that they're compatible with one another and with the multiplication operation. And we need to look at the two operands for our assignment and make sure they're compatible with each other and with assignment, right? Make sure that assignment knows a way to assign an int to a float and what kind of conversions have to take place. Actually, back on that note, if we get into more complex expressions, again, if we had something like, let's say x was our int and y was our float, then we'd be going through and saying, okay, well, when it carries out that multiplication, it's going to have to look at this and say, okay, I've got an int times a float. What should I do? It's probably going to say, well, I better do floating point multiplication. It'll convert the int to a float, carry out the floating point multiplication. So now you've got a floating point result over here. And then it's going to say, okay, now I've got a float that I need to assign to an int. And so I'm going to have to figure out what kind of conversion to apply to take care of that. So again, you have to be aware of the sort of conversion sequence associated with different operations and how that's going to compound in more complex expressions. All right, which brings us to the whole idea of type checking. And again, if we've got a statically typed language where we can do all of the checking at compile time, that's kind of ideal in one sense because we know when we compile it if we've got any type errors in there, right? We can fix them before the program actually runs. On the other hand, if we're doing dynamic type checking, where the types aren't set until runtime and so we can't check them until runtime, then either we've got to have code inserted to carry out that type checking by the developer, or code inserted by the compiler to carry out the type checking, or just let it crash when it hits an operation where the two data types aren't compatible with the operator. So there is certainly a set of trade-offs involved in whether or not we're going to apply static or dynamic type checking. Just in terms of the static checking, there is this reference to languages being strongly typed. And the idea there is it's strongly typed if all of your type checking, every bit of it, can be done statically at compile time. And it's weakly typed if that's not the case. So most languages are actually weakly typed to greater and lesser degrees. Most common languages provide you with some mechanisms that let you kind of get around the static type checking. C in particular gives you all sorts of ways to bypass the type checking. You've got unions, you've got typecasting, you've got the use of void pointers, all sorts of ways that you can kind of backdoor things and get around the type checking and take a string value and try and assign it to an int. And we'll take a look at some of those in the labs and in some of our other exercises. But there's all sorts of ways that you can get around the so-called static type checking in C. And of course, therefore, also in C++. All right, one of the things that we want to think about in terms of our type checking is if we've got static type checking, so if the compiler is going through and doing the type checking for us, how is it actually going to decide yes or no, are these two types the same? So there's two different approaches that we'll take a look at. One is where every data type has a name, and all we'll do is, if they have different names, they're different data types. Right? So if I create a data type for distances, and if I create a data type for temperatures, and both of those under the hood are just floats, if I've got my temp data type and I've got my distance data type, then those two are different data types because they've got different names. And so if I declare x to be of one type and y to be of the other type and try and assign x to y, then under named type checking, it's going to say, no, those things aren't compatible because their type names are different. On the other hand, you can take a structural approach to type checking where you say, well, Under the hood, they're both floats, so there's no reason why I can't assign y to x or x to y. So structural checking looks at the composition of primitive data types and just uses that as a way of saying, are these things the same type? So if, for instance, we create a struct named foo, so again, our structs are just a definition of a data type that say, okay, I've got this composite data structure that's made up of, in this case, an int and a float. And so my struct type is named foo, it's got an int field named I, and it's got a float field named f. And I'm going to create a variable x that's of that type. And then I've got another kind of structures named blah, and they've got an int field named a and a float field named b. So structurally, you can see that these things are the same, right? They're the same composition of the same data types. They're just using different names. So under structural type checking, our x and y variables here would be type compatible, right? Because they've got the same composition. But under named type checking, they would not be compatible because they've got different named types, right? Foo versus blah. So again, you want to be aware of which form your language is using. And obviously, there are advantages and disadvantages both ways. For name-based type checking, it's easy for the compiler to go through and check the data types. It just compares the names. If they're different names, they're different types. Quick and easy. It also gives the developer a way of ensuring that they don't accidentally mix and match types. Again, if we take the distance versus temperature example, if I had my variable x that was a distance and my variable y that was a temperature, then one would expect that I probably don't want to assign the temperature to the distance, right? So we've got a way of using our named type checking to get the compiler to do those checks for us. And just say, hey, wait a minute, you're trying to assign a temp to a distance, and that doesn't make any sense. On the other hand, there might be places where you go, well, maybe in some formula, it makes sense to use both the temperature and the distance as part of some computation. If you think of mass and acceleration as might be different data types, but obviously we can wind up using them in different formulas as part of some computation. So you want to think about whether it makes sense to have name-based or structurally based type checking and what the implications are for you as a programmer. All right, I think those are the key points I wanted to deal with for type checking for now. We'll get into some other fun and wonderful issues next time.